Here's part 3, question 26 on the key. So this says the best Lewis structure for H2SO4, which is sulfuric acid, has zero formal charge on all atoms. Sulfur is the central atom, so let's put an S down. There are no bonds between S and H, so the H's are going to be connected to oxygens. Now I've just happened to have seen a good number of Lewis structures for acids, and H's are going to be connected. They're not going to be connected to each other, and they typically are not connected to the central atom if there are oxygens around. So you're going to kind of have to draw this out, and hopefully you've seen some examples by doing your readings and kind of just doing some studying and all that. H2SO4, let's count up our total number of valence. There are 2 hydrogens, so that's 2 times 1, plus sulfur is 6, and there are 4 oxygens, which is another 6. That's going to give us 32 valence electrons to use. Now let's put our atoms down. Oxygens are going to go around the sulfur, because sulfur is a central atom and there's a lot of oxygens you got to put down, but it explicitly says S and H are not bonded, which is something that I just happen to recognize from seeing acids, but hopefully that clue tells you that it's not gonna look like this hot mess. Don't do this. No. Those H's are gonna go connected to the oxygens. They're also not gonna be connected to themselves too, so don't do that. So here we have it there. All right, that's our structure. Now, it's really just a sulfate ion with 2 hydrogens attached to it, like that. So let's draw, first connect everything. So 1, 2, 3, 4, 5, 6. I just used 6 lines to connect everything. And that means I've used up 12, because remember, every line is 2. So I've used up 12, and that gives me 20 remaining. Those remaining 20 electrons are going to have to be spread out. Remember, once H has its bond, it's done. Never put dots on H when it's in a bond. Do not start doing that. You'll be wrong. But what you can do, is you can put those dots around the oxygen. So 1, 2, 3, 4. That oxygen's done. 5, 6, 7, 8, 9, 10. That one's done. 11, 12, 13, 14. That one's done. 15, 16, 17, 18, 19, 20. Good. You used up all 20. You got 0, which is the goal. Now, since you're at 0, well, actually that's it. There's nothing else to do because you don't have to make any special bonds. Now, let me think about this. Oh, okay, I see what's going on. It does say that it has 0 formal charge. So this would be a theoretically acceptable answer. But because it says that there are 0 formal charges, you got to fix the formal charges. Let's go through right now and calculate the formal charges. Valence minus lines minus dots. So how many valence does hydrogen have? 1. How many lines? 1. How many dots? None. So whenever hydrogen has its single line, it has a 0 valence. So we can duplicate that left and right. Those top and bottom oxygens are also equivalent in their structure, so we can do that here. 6 minus 1 minus 6, that's -1. So, So that means that the top oxygen has a formal charge of -1, as does the bottom oxygen. Well, we don't want formal charges, so we're going to have to fix that. These oxygens in the left and right of the sulfur are going to be 6 minus 2 lines minus 4 dots. They both have 0 formal charge. So we have 0, 0, that, blah, blah. Now, the sulfur in the middle also has 6 valence. So 6 valence minus how many lines? 4, touching it, minus how many dots? None. That gives us a formal charge of +2. So the overall formal charge, on a sulfuric acid molecule is 0, because if you add them all up, 0 plus 0 plus 0 plus 0 plus -1 plus -1 plus +2, all those charges add up to 0. So far, so good, except remember, we need to get rid of the formal charges. That means you need to probably push electrons towards sulfur. Whenever you want to think about formal charge, you can kind of think of it as formal charge will go up, which we want. We want -1 to go up to 0, right? So formal charge will rise when you push electrons away. Formal charge will fall when electrons are pushed toward it. Because remember, you're adding lines. So you're adding bond order to it. So let's do that. Remember, you can't add or subtract lines or dots without converting one to the other. So let's convert this set of lone pair. It doesn't matter which one I pick on that oxygen, but let's convert one of those lone pair sets to a multiple bond. Boom. Now, if you calculate your formal charge again, for this oxygen and the sulfur, because those are the only two affected so far. Then this oxygen on the top has 6 valence minus its 2 lines minus its 4 dots. So far, we have fixed that formal charge. Formal charge on the top oxygen is 0. Sulfur's new formal charge is +1, which you can verify by doing valence minus lines minus dots. 6 minus 5 minus none. Now, it's better. It fell as I said it would. It went from +2 to +1 because I pushed electrons toward it from oxygen on top. But it's still not satisfactory. But you kind of see a clue here that we can do the same thing on the bottom oxygen. So let's take some electrons from here. Let's do that one, and then add a multiple bond. That'll get rid of this. And boom, we have all 0 formal charges everywhere. Now get rid of the formal charges because this is extra. Now what does the structure say? The structure of a 0 formal charge sulfuric acid is, well, we got 1, 2, 3, 4 singles and 1, 2 doubles. This combines a lot of different concepts, but hopefully that kind of clears up what was going on, because this question's kind of tricky. 27. A nitrogen-oxygen bond and the NO2 plus has what bond order, what bond length, and what bond energy than the nitrogen-oxygen bond at NO2? Well, you know it's probably going to have to happen. Draw it out. We drew out NO2 before. I don't remember what it looks like, but it looks something like, we can figure it out together. So it's 5 plus, there are 2 oxygens, so it's 2 times 6 for its valence. Don't forget to subtract 1, and that's basically 4 plus 12 is 16. So there are 16 valence electrons in our drawing of the NO2 plus. So put 1 in there, then, or N in the middle, O's on the outside, bond them once, we use up 4, that gives us 12. Add those 12 on the outside, that gives us down to 0, which is what we want. But our nitrogen is deficient, so we're going to make a double bond on both sides. Now, what we basically have here is a double bond on both sides of the N. Now, verify the formal charge. I'm going to do that real quick. 0, 0, plus 1. Okay, yeah, that's right. All right, so that's going to be NO2. Let's draw NO2 minus, which is the nitrite ion. So that's going to be, let's see here, 5 from the nitrogen, 2 for, or 6 times 2 from the 2 oxygens. And now we're adding 1 because this is a minus charge. That's going to give us 6 to 18. Now we have 18 valence electrons to use. I'm going to move this up. Ooh, I did not select them all. I'll move that up and out of the way so you can still reference it. So now we're going to do N again in the middle, 2 O's on the outside, but now it's going to look a little different. So we have our 2 bonds there, subtract 4 because each bond is 2. It's going to give us 14 valence electrons to spread out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've run out of room on the outside, so put the remaining ones on the inside. Now, our nitrogen with those two straggling electrons still doesn't have an octet, so one of the oxygens in this case will share. I'm going to pick the left one, and now that is what it is. Verify formal charge, -1, 0, 5 minus, 0. Okay, cool. All right, so here are our 2 molecules that we need to compare. We have this one, and I don't have, if we really want to be fancy about it, I guess I could put the bond thingy on it. Let's just do that for the sake of being complete. Remember that Lewis structures, when there's a charge, should have charge in the brackets. And now you can see the difference. All right, thinking about them. Nitrogen, the first one, has what kind of bond order, what kind of bond length, and what kind of bond energy compared to the second one. So we have a double bond. This has 2 double bonds. This has a single double bond, and this has 1 double bond and a single bond. So the first one's going to have a higher bond order simply because it has more double bonds. So this has a double. I'm going to say this has a double bond and a double bond. That's one on the bottom has a double bond and a single bond. So for that reason alone, it has a higher bond order. Now, what about the overall bond length? Remember that you have resonance structures, so they all kind of exist in this state between, right? Now, remember, double bonds are shorter than single bonds. So if you kind of take the average, right? 2 plus 2 divided by 2 is 2. I almost forgot for a second. And then here you have a 2 plus a 1, double bond plus a single bond, right? And then we're dividing that by the two locations at its end, and we have a 1.5. So this is a higher bond order than this. Now, when the bond order is higher, the bond length is lower. Because we saw earlier that, remember, single bonds are longest and weakest, and then double bonds are shorter but stronger, and then triple bonds are the shortest, strongest. But we're just looking at double and single here, and we're really looking at the bond order, which is like somewhere in between. So long story short, the higher the bond order, the lower, or shorter I should say, that's what it has here, the shorter the bond length. And then what about the bond energy? So as we kind of already saw, a higher bond order is going to be related to a higher bond energy. Think about how much energy it takes to break a single bond versus a double bond. Breaking, let's say you wanted to break everything. If you wanted to break the NO bond here and the NO bond here, you have to break a double and a double. That's going to require more energy than breaking a double and a single, which is why it has a greater bond energy as well. Just make sure you review double, single, triples, and like bond order, and the fact that the general idea is higher bond orders are shorter, and they have more energy required to break them. They contain more energy between them. How many resonance structures are possible for the carbonate ion? Resonance. All right. So like, if you were to draw out the carbonate ion, let's see, it's going to be 4 valence plus 3 times 6 plus another 2. That's 24. So you have carbon, 3 oxygens, and we're going to connect them all once. 1, 2, 3, 4, 5, 6. That's going to take away 6. We're going to get 18. We're going to find that you can spread them out all around the edges, taking you all the way down to 0. However, the carbon is electron deficient, so one of these oxygens is going to do the duty of sharing in. This is one of your resonance structures. Every resonance structure will have the same number of electrons as every other one. They're not like completely different things. They're just different versions of the same thing. So here you have a carbonate. Let's be fancy in particular. I'll put the charge thing around the edge. Here you have a carbonate. And to verify, let's just check the formal charge real quick. Valence minus lines minus dots. That's 0 for this, 0 for that, -1 for this one, -1 for that one. Okay, good. So that adds up to -2 overall. All right. Now that's one possible resonance structure. Where you can ask yourself, where do electrons go? I remember learning in organic chem that if you want to give every one of these oxygens like an identity, like this is oxygen A, oxygen B, and oxygen C, every one of these oxygens is literally a different atom. So whenever a different bond exists, that's technically another resonance structure. And I remember learning that bonds basically hop over atoms. It's like they swing around like a door hinge. So another resonance structure that's acceptable is this one. I'm going to shrink and then duplicate. So here's another one. By the way, there are 3. But here's how they look if you're interested. So when that electron pair swings over, it changes that back up to here, and then this goes back down to 0. And basically, a resonance structure is a structure you could reasonably draw. Different people can draw different resonance structures, and they all are valid to an extent. So that's what this one looks like. Notice how this is a bond between the carbon and the oxygen that's labeled as C. And then we could have another resonance structure. Let's say that the electrons swing this way. We have over here, and it's going to look like this. Okay, good. So those are all the resonance structures. Resonance structures typically have those little arrow thingies going between them. And that's what's valid, because when you did the Lewis structure, you didn't put any lone pair on the central carbon or anything like that. So that's what it is. Basically, when you're figuring out how many resonance structures are possible, just kind of like see how many ways could I draw this without changing any of the formal charges overall, because you still need the overall charge to be -2, and you also want to make sure that you're not putting any lone pair on atoms that never had it in the first place. Types of atoms. Carbon never had lone pair, so don't go putting them on there. That's one way to figure out how many resonance structures are possible. All right, for predicting the structure of SOCl2. Okay, I'm gonna draw this out. It's looking a little weird here so far. All right, so SOCl2, to count up our number of valence, it's going to be 6 plus 6 plus 2 times 7. That's 12 plus 14, which is 26. So we have 26 valence electrons to use. S is going to be in the middle. Oxygen's on the edges. This looks like it might have a mistake. I don't know if your professor told you this was a mistake or not, but there's no way this can be bent. Perhaps the question was changed. But anyways, let's figure out what the actual shape is. So of our 26, we are going to use up 6 to connect them once. So -6, and that's going to give us 20. Now those 20 are going to go all around the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Ran out of space. 19, 20. Good, we've used up all 20. So we hit 0, which is exactly what we want to do. So once you hit 0, you don't really need this junk anymore. Now you're going to do the thing where you count out the number of electron regions, also known as electron groups. This central atom around it has 1, 2, 3, 4 areas of electron density. So there's 4 electron regions. That means that the electron region geometry, or electron region geometry, electron geometry, there's so many names for things. That can be really confusing too if you're studying for this, is tetrahedral. Now, what are those electron regions composed of? Well, one of them is a lone pair. There's only one lone pair. And then another 3, this one, and that one. Those are all bonding areas. So there's 3 bonding areas. And that makes sense, and that gives you an overall molecular geometry code of trigonal, pyramidal, or pyramidal. Yeah, maybe this was I think this was a mistake, because SCl2 would be bent, but SOCl2 would be trigonal pyramidal. So if you want to bring that up to someone, you can do that. Let's find SOCl2 and see if it's actually in here. It's not, but you could build it yourself. So let's do that. It would be a single and a single and another single and a lone pair. And that's what it would look like. Now, of course, it can have a slightly different shape if you want to minimize thermal charge. Let's kind of figure that out real quick. -1, 0, 0, +1. Okay, so the better structure if you want to minimize formal charge, which is not going to change this answer at all, by the way. But if you wanted to kind of do another alternative but acceptable structure, it would be S double bond O, single line, Cl, Cl, 1, 2, 3, 4, 5, 6. Oh no, not that. 1, 2, 3, 4, blah, 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 blah. Okay. So this is acceptable as well. If you calculate the formal charge, valence, that's 0, that's 0, that's 0. Valence minus lines minus dots for the sulfur, 6 minus 4 minus 2. All right, that's also a good structure. It doesn't matter whether you add a double bond or not. It's still going to be trigonal pyramidal. So I think that this question probably should have said SCl2. Here's how I know that. Let's draw out SCl2 real quick. That's going to be 6 plus 14, that's 20. SCl, bond them once. To use up those 20, and I only have 16 to use, right? Because I just used 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That is bent. Because here's what it would look like. So we'll get rid of that. Add this. This is what it would look like if it were SCl2 without the oxygen. But the oxygen does mess it up, and that's why the answer is not correct on the key. All right. And then 30. Okay, good. Number 31 we have to do. Yay, last question. So 30. Consider the following molecular shapes and match them with this is the example I used earlier. I can tell the future. BF3 versus NF3. Well, we know already that BF3 is trigonal planar, because if you draw it out and you remember that boron does not need, it can live a nice happy life with just 6. BF3, it looks like this. B with its 3 F's, and you got your lone pair all over the place, great. But this is what it would look like if you do it correctly. In contrast, what NF3 would look like is if I replace this B with an N, there's also going to be a lone pair on there because it has a different number of valence electrons. So if you kind of build it and match it, NF3, and here's a clue by the way, this N could also be a P. Nitrogen and phosphorus both are going to behave similarly because they're in the same family. Also, these halogens on the edge could be any halogen. It could be chlorine or bromine or fluorine. They're also going to behave similarly. So in theory, that could be, so NF3 and PF3 and PCl3 and PBr3. Basically, I'm just saying, what if I replace N with P or P with N, and then any halogen with any other halogen? I could do PH3 because hydrogen kind of acts like the halogens with a single bond. There's so many different possibilities. It doesn't even matter. They're all going to form a shape we know as trigonal, but it's not the flat one. There's trigonal planar, which is flat. This is that one. This is trigonal planar. But it's not trigonal flat, it's trigonal distorted. So we would call that trigonal pyramidal or pyramidal. And that's what this is going to be. The reason is there's a lone pair on that central atom that's going to push all those other atoms down. There is no lone pair on the central atom for trigonal planar. So that's kind of one of the things that really helps you. So this, trigonal pyramidal. This one, trigonal planar. Now the names aren't there, but the reason that you can get this question correct is you play around with like the VSEPR theory and realize that when there's a lone pair, you get that like weird tripod type of situation where like these are like touching the plane, so to speak, and then this is like raised above the plane. As opposed to if you have this, all the atoms are sitting in the same plane and it's not raised above it. This site is really cool. Just basically look up PhET molecular shapes, and you can play around with them and build them yourself. So if we were to build BF3, it looks just like this, trigonal planar. No lone pair on it. If we add a lone pair, suddenly it's not flat. It has that little tripod looking shape. If you want to see real atoms at the bottom, click on real molecules, and these are such common examples. You can see BF3, flat. NF3 is not on here, but it's going to act just like NH3, which is not flat. So that is how that works. And hopefully that helps with the test.